saving videos right now is about 1 and 2. So fingers crossed this one will save. If it saves, I can put it in Canvas. If it doesn't, hopefully you've got a good memory and you'll get most of what I'm doing. In general then, before we get started, is there any questions for the good business that you want to answer? Okay, that's a good sign. Are you looking, oops, here somebody just turned up. Are you looking at the full screen with my hand wiggling up and down? Okay, so let's get started. We are going to be trying to show you and to deal with concepts like vector functions, vector fields, and gradient vectors. So we are going to expand today your world on what is a function. So that is a function, 141 function, no biggie. You give me an x, I'll tell you what the value of the function is. To be a function, for every x, there can only be one answer. Can't we also write this down as y equals x squared minus 1? And if we drew it, its graph would look like that. We are all, or should all, be really comfortable with essentially two-dimensional functions, right? X and Y, two-dimensional picture. Here is a function. This time you tell me an x and a y, and the answer you get in this case is x squared plus y squared. You can also write this guy down as x squared plus y squared. Has anybody got any idea, and I guess it's asking a lot because it's not that obvious, what does this thing look like if you sketch it in 3D space?
Parabolic cone.
Wow, well done. Yes. And I am pretty impressed because that kind of sort of looks like it. Because normally when I draw things, especially when I try and draw them in 3D, they look very bad. Which is weird because I have a really good 3D brain, in my opinion. I see things visually. I'm a visual learner in a lot of ways. So I can visualize things. I just can't draw the darn thing. It's very frustrating that I can see it in my head, but I can't put it on paper. So I'm kind of pleased whenever I get things. So I know that when I'm doing 3D stuff, I just imagine surfaces, and that's fine. Now you can extend that idea, but they are all functions. Now what makes both of these functions is that when you stick in x and a y, you only get a numeral answer, right? You only get one answer, right? A number, right? Mm-hmm. Yeah, so, I mean, if I went and said f, x, y, z is x plus 2y minus z squared. And I wouldn't try and draw that because it's a fourth dimensional surface. But when you type in a number like 1, 2, 3, doesn't the answer you get end up being just a number? So what makes it a function is for any given value of x or xy or xyz, the answer is a single dimensional number. That is what functions look like. So what does a vector function look like? Because that's the new guy, the guy we've never seen before. Here is an example of a vector function. You put a little arrow above it to mean it's a vector. Although typically textbooks just make it bold, but we can't draw bold. Now, do you notice that for any given value of x and y, the answer is a vector? Right? So what does that look like? Well, it means that your answer is unique. It's a vector. It's only one vector for every x and y. But what does it look like? Well, if you try and sketch a vector function, you will generate what's sometimes called a vector field. It's just its picture. And drawing them is notoriously laborious. So I am only going to do a real one once and then say there are great software out there that you plug it in and it draws the pictures for you. But imagine we just take little snapshots. So each one of these guys represents one point in space. For instance, see that guy there? He is the point whose x-coordinate is 1 and whose y-coordinate is 1. Now, if you find the vector function at 1, 1, the answer you get is 1 squared and 1 plus 1. You get that guy. Now, at that point, you draw a vector 1, 2. Remember, that means 1 along in the x and 2 up in the y. So can we pretend that it's roughly that guy? And you try and draw it in the middle because it's representing a kind of snapshot at that point. Now, what would the value of the function look like at 1, 0? Well, it would be x is 1 squared and 1, so you get 1, 1. So you get a vector that might look something like that. What about 1, -1? Well, you get 1 squared, 0, which would look like that. And then if you found 1, -2, you'd get 1, -1, and you get a vector that looks like that. Now, the rest of the ones I'm going to do are not correct, but I'm going to pretend that they are, because I'm not going to calculate them all, or else I'd be here all day. Can you imagine going through all 25 of those different guys and evaluating them all at those points and then drawing a little baby vector at every single one of them? That's the visualization of a vector function. Do you see a vector function?
Looked at a couple of them in Calc 3 too.
You may have seen them, so hopefully it's not a total mystery. But you can, yeah, you did. I think there's like 4 questions, so it's really just a taster, isn't it? You never really did anything. You might have got to draw one, you might not.
Yeah.
You're never going to get to draw one. They take, if you had to draw that really properly, because that's just made up, right? 20 minutes at least, right, for just one picture, if not more. So we just say, okay, software, great. I know what it is. I can get that. So a vector function, which is this guy, generates a vector field this guy. Now, what is the use of these? Well, you know, we had these before we had a use for them. In other words, some scientist came along and says, hey, I need something that can do this. And we said, hey, look at this. Maybe this is what you're looking for. Can you imagine what this could be used to represent? Couldn't this be used to represent water current, right? The surface of a water and current. Magnetic fields, wind forces, smoke blowing over an aircraft's surface. Can you see that a vector field is a very good way of modeling something like that? In fact, if you've ever done differential equations, sometimes differential equations start life off as something to do with a vector field, and then you're trying to represent it. So you can see this is a what's the word I'm looking for? This is at the cutting edge where mathematics and engineering kind of meet. Because I can imagine a lot of situations where you would want to be able to deal with pictures where you've got forces changing depending on the location of the object in 2D space. Now you can actually do, this particular one is a two-dimensional vector function, and this is a two-dimensional vector field. If you wanted to do a three-dimensional one, there'd be a guy here, comma, a guy here, comma, a third one, right? And these vectors would be three-dimensional vectors. And nope, I ain't going to even try and draw that. But can you imagine in 3D space, the point 1, 2, 3, and at that point there'd be a three-dimensional vector in it. And then when you get to that stage, you're really modeling very dynamic situations. And I could imagine them trying to model a hurricane. And at each point in space, you would have a vector representing the direction and the velocity of the wind at that one point. Can you imagine that would generate a vector field that's kind of good at predictions of what will the velocities look like at a certain place and what direction will that wind be blowing, right? So that is, that's the kind of the foundation behind what these things are. I don't want you just jumping right and say, oh yeah, it's a math thing, you do this, you do that, you move on. It's good to know that these things can actually be very practical. Now, special kind. Can you remember a question that went something like this? There's a fella called Delta F. Can you remember him? Well, let's put a guy in it. Let's call this guy x squared plus y squared. Remember Delta F? Are we back in the day? No. Gradient. The gradient, yes. Well done, the gradient. It's basically this guy. Remember we did that? And this is a good example of a vector function. Do you see you plug in x, y, and you get a vector as an answer? So in this case, your vector function ends up being that. So a lot of the questions that you're going to get in your first set of, from this new chapter, is going to be to find the gradient vector. The gradient vector is just the name we give to this thing, right? You take the gradient of the function in x and y, we call this guy the gradient vector. Now, if you draw a picture of this guy, and I'm definitely not doing it this time. Can you pretend it looks like that? And if you did draw a picture, that would be called a vector field of the gradient vector. Right? The word vector field is just, this is the picture that you get if you use this fella here to tell me what the vector would be at any given value x, comma, y. Cool. So let's do practice at just getting gradient vectors. So here is my first fella. Just randomly picking a function. Its gradient vector, partial derivative with respect to y. So guess what? We're back to differentiation hat on, right? We've been doing integrating for quite a while. We may have got a bit rusty on partial differentiation. If you do a partial differentiation on this guy, you get 2x, and this guy, nothing. And then if you do it, let me re-say that. With x's first, you get 2y e to the x. Then y second, you get 2x plus nothing. after my second attempt. Are we all pretty comfortable with that? So, question?
No questions.
We're good. Right. Apart from my little hiccup, I got my X's and Y's jumbled up in my head there for a second. Right. Well, what happens if we up the ante a little bit? So let's get the gradient vector. Before I start this question, let's look at some properties that are going to reduce my workload. This function is symmetric, isn't it? So if I find fx, can't I just figure out what fy is by symmetry and not do it from scratch?
Yep.
Right? How do you do that? Switch all the x's for y's, switch all the y's for x's, and write down what you got. Right? That's the trick in symmetry, right? If you can do one, you can do both. Which I like because it means I do half as much work as I might have to do, right? And anything that reduces your workload is good. Unfortunately, the function that we're going to differentiate is not pretty. And I've decided to change the square root into x squared plus y squared by half. That is pretty obvious that you need to do that anyway. There are two approaches to this. Both are correct. You might like approach one. Other people may choose to do approach two. Give me any technique for differentiating that. There are two techniques you could use.
U-sub?
Well, that would be good, except for in differentiation hat on. And U-subs are only good for integration.
Use the quotient rule?
Quotient rule, yeah. See, you've got to put the right cap on, right? Differentiation cap on. Quotient rule, totally fine with that. If I did the quotient rule, won't I make this fella F? I'll make this fella G.
Yes.
So we'll do that one, and then I'll talk about the other one, because you might want to do the other one instead. So if I can just move this to the top of my page, my original function is x plus y over x squared plus y squared to the half. And we've decided, which is pretty common, right, to do what you need to do. Now, at the side here, I'm going to put down the top, which is x plus y, and the bottom, which is x squared plus y squared to the half. Sorry about that being a mess, but it is f. Right. If you want to find this fella here, its derivative, then you do f dash g, take away f of g dashed over g squared. At least that's what it would look like back in Calc 1, right? Right, if you differentiate with respect to x, don't you get 1? Right, if you differentiate x plus y with respect to x, you just get 1, right? Now this is the messy one. Do you realize this is going to be a chain rule? Not even a pretty chain rule. It's going to be 1/2 x squared plus y squared to the negative a half times something. What do you get because of the chain rule? Times
2x.
2x. Now, while we're at it, don't the half and the 2's cancel? And I'll just call this x squared plus y squared to negative a half.
Would
So
that
here it goes.
be in the partial of g with respect to x?
It is. Thank you. And pretend I never did that question. I'll start again with the right pieces. It's what I get when I'm 2 lines ahead in my brain. I ain't good enough to do that. Now, you don't need to write this as I'm just repeating myself, but this time I'm going to try and make sure I repeat myself correctly. There we go. This guy is 1. And if you take this second guy, you do get what I wrote. Right. So I put the wrong labels on them, but I was doing the right thing. So it is the same question. Right. Now here we go.
X?
Say again?
G of x equals 2x?
Ah, but times a half and they cancel out and you get an x.
True.
So what we're going to do is f dash g take away f of g dashed over g squared. And I'm going to have to write it here because it's pretty big. F dashed is basically 1. G on its own is that guy. Take away f on its own is that guy. And g dashed is essentially that guy. All over this guy squared. Well, if a half power and you square it, you basically double the half and you get a 1. So when I look at this fella here, that's what our first partial derivative looks like. Do you think I'm going to leave it like that, or do you think I have some work to do to make it look pretty? I know what you want. You want to leave it like that, but that's not the choice. You have to fix it. Right? You have to simplify it. And there is some simplification going on here. This term here is basically just x squared plus y squared to the half. This term here has an x squared plus y squared to the negative a half. That means that they share a common factor of x squared plus y squared. Now here's the problem. These are the common factors. One is a negative half power, the other is a plus half power. Which one is the common factor? X squared plus y squared to the half or to the negative a half, right? One of them is the thing that we're going to suck out as the common factor.
Negative half.
Always the smaller. Now, that's a bit weird, but it has happened before in other cases. If you take a half power and you remove a half power, isn't it like adding a half power? So what you end up with is x squared plus y squared to the power of 1. And this guy, you take away. Use this fella up and you take away an x plus y.
Don't forget the x.
Ooh, thank you. Now this fella comes downstairs and now you have 3 halves. This guy is x squared plus y squared. Take away an x squared, take away an xy. So what you left with, a y squared, take away an xy. That looks pretty cool. That is one of my 2 pieces.
It's a lot of work. Do we have a simpler way to do this?
Not really, I'll show you the other way, but I don't know if it's any simpler, it's just different. Now, the first answer is this guy. We should be able to figure out who the second one is by symmetry. Right, if this is fx, won't this guy be x squared? Take away, instead of take away xy, it's technically take away yx, which is still xy. And the bottom ends up being the same. Because if you switch the x's and y's, you don't switch anything. So you end up with that. So now we're in the nitty-gritty of an ugly version. So we've seen a nice easy version would be, you know, find the gradient vector for x squared plus 2x. Right, that'd be an easy one. Now we're looking at really ugly one. Now, I promise you there's 2 ways to look at this question. So here we're way back to the beginning. And I said there was 2 ways to tackle this question. If you rewrite it like this, I won't use the quotient rule. Agreed? What rule will I use to differentiate this?
The chain
Product.
rule.
Product rule, really, with a little baby chain rule inside it, but essentially a product rule. Now, I don't know, maybe product rule just works better in your brain, and that's fine, because both are equally horrible. You might want to try a question doing it as a quotient rule, and the next fraction question doing it as a product rule, and see which one kind of works for your brain and your algebra. Right? We cool? About to call that one gone? Right. So we're just focusing on finding gradient vectors. Well, let's put a trig in. Nothing too scary. Let's put that fella in, right? And let's get the gradient vector. If you differentiate this fella with respect to x, don't you have to use a product rule? X sine of xy, it's a product rule. So f dash g plus f of g dashed, which is the cosine of xy times anything. If you differentiate the sine of xy with respect to x, what will you get?
Y.
Yeah, times another y. So I'll squeeze it in here. Don't have enough room, comma. If you want to differentiate this guy with respect to y, it is not a product rule, because that x is just a constant. You're simply just going to get x, the cosine of xy, times another x. So what do we have? We have the sine of xy plus xy, the cosine of xy, and then the other term ends up being, I believe, an x squared, the cosine of xy. So you see in that case it wasn't too onerous. So which ones are going to cause you trouble? Anything with a fraction in it, anything with a square root and a fraction in it, right? So you put those together, you basically get that guy. Second, look out for symmetry. If there is symmetry, you can use it to half your workload. Because remember that ugly one we just did before this? Once I did the first ugly one, wasn't the second one just a matter of switching x's and y's and I get it for free? You don't want to have to do, unless you have to, 2 of those questions. Well, let's expand our process. Suppose f, x, y, and z, right? So it's a function of 3 variables. And it's x squared plus y squared take away 2z cubed. So I'm making it nice, simple. The gradient vector is now expanded to a 3-dimensional vector, right? One with x, one with y, one with z. In this case, 2x, this case, 2y, in this case, negative. So can you see that you can extend a gradient vector beyond just x and y's? Couldn't you do x, y's, and z's and keep going forever? I think the textbook only goes as far as x, y, z, so I'm not going to go anywhere. Everything that we just did, you could do a 3-dimensional version of the same thing, right? Just add some z's and z cubes and cosine z's and whatever. And you're basically same process, but 3 times instead of 2. We cool? So this is pure algebra, right? Just differentiation, partial differentiation with respect x, y, and z of some given function. Life is cool. So here's a problem. Suppose I have a vector function f of, oh, let's make it simpler. Let's do a vector function of only 2 dimensions, f of xy. If there is a small function, a little f, that has the property that this guy is equal to that guy. So can you imagine there might be a function that looks something like this, whose gradient function is the function f, right? Imagine that concept. We have a name for this. The little function, this fella here, is called, get its name right, a potential function. For f. Now, if you can find a little f that has this property, which is actually kind of hard to do, but it is possible. If you can find a little f that has this property, that its gradient is this cell, then you are looking, and we describe these guys as a conservative vector field, or conservative vector function, I should say. Now you might wonder what on earth is going on, why they got these new names and why we're doing this. The best analogy I have got is, remember when we did Calc 1 and we moved into Calc 2? Remember that transition? Didn't we start off thinking of integration as the opposite of differentiation? How to undo antiderivative, right? That was the original name, right? We kind of dropped that name pretty quickly, just called it integration, but that's where it started from, right? So can you imagine what we're going to do now is that we're going to look for essentially the integral of a vector function. We're going to try and find a function that you would get, right, if you work backwards. Right? And that process is going to allow us to think of and expand what we mean by integrating things. And you're going to find that the next section gets into that in a lot more detail, but the next section deals with what are called line integrals. That's its title. And you think, well, I know what an integral is, at least I know a Calc 2 integral. I know a triple and double integral from Calc 4, right? I know those guys, right? I've seen those guys. So what's a line integral? And you'll find out that those things are really quite important. So I'm not going to do that today. That's going to be another lesson. I'll talk about one example when I finish this little intro part. But I want you to imagine how these line integrals might work. Here is a very bad attempt, and I'm doing my usual of making no attempt to be accurate. But can you imagine that's a vector field, right? Okay. And you do a curve. I know it's called line integral, but basically it's curves. Line is just an example. Now, can you imagine an object traveling through a vector field? In this case, that guy there. I'll call him C. C for curve. When you calculate the line integral, what you are calculating is the total, or one of the ways to think about it, is the total amount of work that you had in traveling your boat from here, let's say that's a start point, to here. So you're looking at an integral as work done. That's one of its visualizations. And I can imagine that would be useful, because if you want to know how much energy is used up, if you want to use the word energy instead of work done, I guess, you could look at this and say, okay, if these vectors were really big, wouldn't that mean that the wind was blowing really fast? And sometimes the wind's giving me a really good help, right? It's shoving me along. So I'm not going to do much work there. In fact, in a way, I'm kind of gaining energy, aren't I? Because they're shoving me rather than me fighting against it. And then at other points in my journey, couldn't I be fighting against the current? And these vectors should have directions on them. Right. So you can imagine that would be a useful thing to be able to calculate. So we need these things called line integrals. Now, for the pure math amongst us, I guess it doesn't matter so much, which is actually me, because the most interesting parts of math that I find are the ones that nobody has got a use for. I don't like math that's practical, but that's me. Other people love math that gets used by engineers. So here's your puzzle. See if we can figure it out. So I got a vector function. And it's equal to that. And I am trying to find a little function f which has the property that the gradient of f is equal to this. So here's our problem. Find the function f, the little f, right? So it's going to be x squared plus y squared, right? That kind of function, right? Just a normal function, not a vector function, that has its property that its gradient is this fella. Now, isn't this fella that guy? Great. So let's try and work backwards. The partial derivative of f with respect to x is x plus y. Agreed? Now, what would you get if you integrated with respect to x? Well, wouldn't x get you a half x squared? What would the y get you? If you integrate y with respect to x, what would it get you?
xy.
xy, yx. Now, normally you would say plus a constant, agreed? When you integrate things, you do plus c. We have to be a bit careful here. Isn't plus a constant in this particular context, isn't plus a constant a function of y? Because y is a constant. So we're going to call this fella f1 of y. So here is my first candidate for f. Now, what do I know about this second fella? He's equal to that guy. Now, what happens if you integrate him? You'll get xy, agreed, minus a half y squared, agreed, plus a constant. What will the constant be if you integrate with respect to y? Some arbitrary function of x. Now, there is my second candidate. Agreed? Now, let's put them together in such a way that both of these things are going to be true. Now, this guy has an xy, this guy has an xy. So you agree the answer has an xy in it?
Yep.
Right? This function has a half x squared in it. Right? Agreed? This function doesn't have a half x squared in it, but couldn't that guy be a half x squared?
Yeah.
So I'll use him. And this fella has a negative a half y squared. Right? And couldn't this guy be my negative a half y squared? So that fella, basically all the bits that aren't generic, these are like placeholders. Do you see this guy, and they're the same guy. So you need one of them. This guy here is my candidate for the solution to that problem. And what was the problem? It said that its gradient should be x add y, x take away y. Well, I should do a double check on that. Is the gradient of this function x plus y, x minus y? Let's find out. If you differentiate this with respect to x, you get y plus x, which is what x plus y is. And if you differentiate it now with respect to y, what do you get? You get an x.
X minus y.
X minus y. Did it work?
Yes.
Yes. So technically, do you know we've just found the antiderivative of a vector function? But it's not as
similar.
Keep going.
Is this similar to the variation of parameters in differential equations?
I don't know enough about differential equations to say yes or no to that. So it could well be. Whenever I get around to teaching differential equations, I'll go back and get the cobwebs out. But I haven't taught that for 30 years, so I'm not going to commit myself. In fact, things have probably changed in differential equations. But does that look as a similar process? In which case, that's great. And if anybody else has done differential equations, does that sound, what he says sounds right to you? Well, let's just say yes for the time being, and hopefully
I think there's quite a bit more to the variation of parameters for diffq, but it's kind of the same.
Kind of the same. So sometimes it might only be the analogy thing that's the same, right? You're doing the same kind of things, but for different reasons. Yeah. But it's kind of a cool thing, isn't it, that you can now find antiderivatives of vector fields. You can find out, and I just looked at my time, and that's pretty much all we have time for today. I'm going to try something different. So goodbye, everybody. It was nice seeing you. I'm going to go out of this, but not close it, to see if I can make sure that it actually saves this. I'm wondering if closing the program might be cancelling the recording. And so I'm trying to find another way of saving it. So goodbye, everybody. I'm just going to disappear and see if I can make this thing work.
Right. See you tomorrow then.
See, oh yeah, that's right. And where we get to do line integrals, which is the only two things you need to do this week apart from get ready for your test.
Yay.
So, that was not enthusiastic. Come on, if you're going to fake it, you should do better than that.
That's why I didn't say anything.
You couldn't fake it, so you were going to try. Okay. Right. Darn it. The one thing I want is in the way of where I want it to go, right? So let's see if I have got this thing saving. Please be saving. I don't want to leave it until then.
Have a good day, Professor.
Okay, we are looking good, guys. I think I'm just going to keep this open for a little while, so bye-bye to all of you, but it looks like it is saving. So I think the moral of the story is don't close until after it's finished saving, which is kind of weird, but I guess that doesn't make sense because that means it would record forever. Okay, I'm going to bite the bullet and just say bye-bye and hope that it doesn't unsave. Okay, bye-bye, guys.
Thanks.